You can all see my screen, right?
Yes.
Okay. Yeah. All right. So in the last class, we set up the problem of specific heats, and the essence of the problem is that if you measure the specific heat, I'm here writing CV, which is the molar specific heat per at constant volume. But CP and CV are, for at least for an ideal gas, they are related as CP minus CV is R, which is the universal gas constant, ideal gas constant. So if you know how CV varies with temperatures, CP pretty much varies the same way. And for most other substances like liquids and solids, CP really doesn't uh, differ too much from CV. So this gives a fairly good picture. And what we saw was that you had some structure like this. And these plateaus are the only ones that can be predicted using classical mechanics. Now, these are a result of the equipartition theorem. And I said that this problem was related to the black body radiation problem. So before we move to the black body radiation problem, while I have only stated the equipartition theorem, today we want to actually kind of give you the underlying principles that uh, go into this equipartition theorem. Okay, so we all so let us consider the process of thermal equilibrium. We discussed this qualitatively. Okay, so the process of thermal equilibrium is, let us say you have a bath which is at a temperature T, and now you take an object which is at at a temperature T, T1, which is not exactly equal to T, and you place it in contact with this bath. Okay, what happens is a very complex set of processes involving conduction, radiation, all these things take place. And if this is a small enough body, if this is a small enough body, and the bath is a big enough bath, then this reaches equilibrium with this. Okay, so if small enough body and the bath is big enough, the body reaches the temperature of the bath. Okay, this is the idea of thermal equilibrium in the particular context of a small body interacting with a large bath. Now, this is an irreversible process in the sense that you always go from the meaning the energy is extracted or given to the small body, but the bath pretty much doesn't change. Okay, so that is the assumption when we say that this is a very large bath. The bath pretty much doesn't get affected by these small changes in the state of the body. Now,
So
yeah,
what do you mean by bath didn't affected by the change of the system? What
yeah.
affecting?
So what we mean is the temperature of the bath doesn't change, but the bath extracts heat or gives heat to the small body. Is that clear?
But if it is attaining equilibrium, the temperature should change, right?
That is what I'm saying. If it is a
I mean,
large enough
both are
bath,
coming into an equilibrium.
Yes, the body is coming into equilibrium with the bath. The bath is not changing. Okay, so that is what is happening. Basically, we are treating the bath as a very, very large system and ignoring any changes that happen to it. Okay, we are
Okay, so the
ignoring
body is coming to the temperature of the bath, but
of the bath.
the temperature of
Yes,
the bath didn't change.
and the temperature of the bath did not change. Yes. Now, but the body definitely transfers heat with the bath. Otherwise, there won't be any thermal equilibrium, right? Hello.
Yes.
Yeah. So according to the second law of thermodynamics, there is a non-zero change in the entropy of this process, right? I mean, this process involves a non-zero change in the entropy, and usually the entropy change according to second law of thermodynamics, since this is, we also said that this was an irreversible process. If this were done in a sort of quasi static way, which we did not really do anything to ensure that it was done in a quasi static way, we this body is at a temperature T, which is T1, which is different from T. So it's a non-equilibrium process. It's an irreversible process. So there is a positive change in the entropy. So the entropy of the body, let us say the body is hot and heat is extracted out of the body. The entropy of the body itself goes down, but the entropy of the bath increases. And the entropy of the bath actually increases by much more, so that the total entropy change of this process is positive. This is what second law of thermodynamics says. Now, what we are going to look at is a very fundamental principle. Okay, so the total entropy change of such a process usually irreversible. When I say irreversible, what I mean is you don't see two bodies that have reached equilibrium going back to their initial temperatures, right? Now, the probability of that happening is astronomically small. So that is what second law of thermodynamics ensures. Second law of thermodynamics ensures that the probability that the reverse process happens is astronomically small, or infinitesimally small rather, and the entropy of the forward process is finite. Sorry, the probability of the forward process is finite, is positive. Okay, the total entropy change of such a process, usually irreversible, is positive. Now, the now how do we, now once the body reaches equilibrium, we now have the entire system in thermal equilibrium with the bath. Okay, they are at the same temperature. Now, what can we say about such a system? Okay, now what can we say about what are the various average values of various quantities, like the state variables of that system? Can we make any predictions when this system is in contact with a thermal bath and in thermal equilibrium with that? Okay, so the question is, under thermal equilibrium, can we make any predictions or quantitative statements about the various physical quantities pertaining to the system? Okay, pertaining to the system. Now, This seems like a very difficult question, but physicists in the 19th century, especially Ludwig Boltzmann and Josiah Gibbs, okay, they Gibbs Boltzmann distribution, they independently and in completely different pathways came to the same conclusion that yes, there is a quantitative statement that we can make about any system which is in thermal equilibrium. Okay. And what is the statement that they made? That the probability, okay, the probability that the system has an energy, sorry, E, okay, at temperature T is proportional to, it's proportional to that the probability that the system has an energy E at temperature T is proportional to exponential of minus E by kBT, where kB is Boltzmann's constant. Okay. Now, I wrote this as a proportionality. Can we say anything? Sorry, Anjaney, what is the question? By allowing what changes in the system, can we make the astronomically small probability of reversing the process sufficiently large to occur in the reverse direction? Okay, so then you will have to actually take the system off equilibrium. If you want to reverse that process, you have to take the system off equilibrium. You have to do a lot of work. External work input is required to reverse such a process. And in most cases, the work required is extremely high, meaning it's thermodynamically a very, very expensive process. Okay, so it's a very good question. And the answer is you need to do work. You need to do work on the system. And usually that the cost of that work is extremely high to reverse such a process. For example, think of this. You mix a drop of ink in water. Imagine how much work. You did not do any work. The Brownian motion inside the liquid took care of all the diffusion and mixing. Imagine you want to separate these two. How much work do you need to do to separate them? In principle, you can separate them, but in practice, it's extremely difficult. Okay, so that's the usual cost that you have to incur when reversing such a process. Okay, so now you have this exponential that I wrote with a proportionality constant, and this kBt is often also written as e to the power of minus beta e. Now beta is 1 by kBt. And it turns out that even though T is the absolute temperature, from a physics perspective, okay, from a physics perspective, beta is actually a more physically meaningful quantity. Even though we are conventionally using T, the temperature, because it is practically measurable and we have physical instruments to measure temperature, to gain insights into some very special phenomena, we'll talk about some of those later. For example, negative temperature. Now we said that there are systems which exhibit a negative temperature. For example, lasers. Okay, when a laser is in this state called population inversion, it actually exhibits something like a negative temperature. Now, what does that even mean? We said that the is uh, absolute temperature has a very clearly defined zero, and no physical system can have temperature less than that. But it turns out that the negative temperature is actually not defined with respect to T, but it's actually with respect to beta. Beta can be negative, okay? Which means it's actually the connection with negative temperature happens across T equal to infinity and not at T equal to zero. It's in that sense. We'll look at some such special systems later on in the course once we, look at quantum physics also. But it's good to keep in mind that this beta is a more physically meaningful quantity, even though temperature it's a more insightful quantity, even though temperature is more practical.
So
Okay. Yeah.
Excuse me, sir.
the KB is positive and T cannot be negative. Then how beta can be negative?
Yeah. So that's a good question. It's actually, we will look at systems where you will see that you effectively you will have a negative temperature. I'm not saying that by this definition of beta you will get a negative temperature and you can equate 1 by kBT to negative temperature and then say uh, uh, T is minus some Kelvin. The way to define it is slightly different. Okay, we will look at that. The example that I gave you is a physical system which exhibits a negative temperature. Okay, a
Okay.
population inverted system is like a negative temperature system. Yeah, exactly. As Sanjay very well put it, negative temperature is actually hotter than the positive one. So we will look at that later. Okay, I just wanted to make this comment because I defined beta. Now, every probability, when you write it as a proportionality, will have a normalization constant. Okay, and this normalization constant comes from the simple requirement that if you integrate, okay, this P of E, or if you sum over, instead of let's sum over all E. The sum over all probabilities, because the system has some energy or the other. So if you take all the possible values of energy of the system, all E, then that should be equal to 1, and that gives you, this defines the normalization N. Okay, this is the most general definition of N. Now, if you have a system, so example, let us say we have a system which has possible energies E1, E2, so on up to En. Then the probability that the system has energy Ei will be e to the power of minus some normalization times e to the power of minus beta Ei. Okay, and N in this case will be summation over all I, or rather 1 by, N will be 1 by summation over all I, P of Ei, okay, sorry, summation over all I, this is equal to 1, so therefore N will be summation over all I e to the power of minus beta Ei. Okay, this particular quantity you will later see that the summation over all I e to the power of minus beta Ei. Okay, now this is, in statistical physics it's called the partition function. We won't actually go into that, so just treat this N as a normalization constant. That is all it is. in reality. Okay, so now I said that this was related. This is a consequence. This principle called the Gibbs-Boltzmann distribution is a consequence of second law of thermodynamics.
Excuse me, sir.
Yeah.
Sir, which is the Gibbs-Boltzmann distribution, the probability distribution or the normalization function it is called?
No, no, no. This probability, that the probability that a system has energy E is proportional to e to the power of minus beta E is called the Gibbs-Boltzmann principle.
Okay, sir.
Okay. And now the system, this is a very crude definition. We'll actually see how to apply this in reality in a minute. So I said that this was a consequence of the second law of thermodynamics. So let us see how Boltzmann derived this Boltzmann's derivation of this formula. Okay, so let us consider a large collection n identical systems. Okay, let us consider large collection of n identical systems. It's usually called an ensemble. Okay, and n is very, very large. N is of the order of, let us say, Avogadro's number, which is a metric for anything, any large number in this universe. Okay, now, and it is isolated with a constant energy. Okay, the entire system, the entire ensemble is basically an, it's a closed system. And we label the systems, we can label the systems as 1, 2, 3, so on up to capital N. Okay, now.
So what do you mean by ensemble is a closed system?
That these systems are not, they are not exchanging energy with anything outside.
Okay.
The total energy of this is a constant. That's what we usually mean by a closed system. We talked about open and closed systems, right? So if the total
Yeah.
energy of a system is constant, it is called a closed system. That is what we mean. Okay. Now these systems can all be in different states. Okay. Let us say we can label these systems 1, 2, 3, 4, so on, like that. Now let us say N1 systems, that is the N1 of these systems are in some state, let us say A1, and N2 of them are in state A2, and so on. Now obviously N1 plus N2 so on up to, let us say there are k states or whatever, it doesn't matter. This summation should add up to n because the total number of systems that we are considering is n. Okay, and if this state A1 has an energy E1 and this state A2 has an energy E2 and so on and so forth, we said that the total energy, okay, that is N1 E1 plus N2 E2 plus so on should equal some energy E, because we said that the ensemble is a closed ensemble, right? Now, if the total n is fixed, this is fixed and this is fixed, the number of ways or, because remember that these systems are all different systems, but they are all identical. Okay, the number of ways or combinations, we all know combinations and permutations, so the number of combinations of the various ni's, sorry, the number of combinations of the various ni's, okay, meaning the number of ways in which we can choose a particular set of occupation numbers, the number of ways to choose or to realize a set of ni's. That is what we are interested in. This will you can do this calculation. It's basically n, choose, let us say n1, we choose n1, and then n minus n1, choose n2, and so on. Okay, and if you simplify this, this will be n factorial by n minus n1 factorial times n minus n1 factorial by n minus n1 minus n minus n2 factorial, n2 factorial, and so on. Now all these things get cancelled, and what you have left ultimately is a term like this. This is, you could have arrived at this in a much simpler way using what is called the multinomial expansion. But in any case, this is the combinatoric factor that we need to consider. Okay. Now, in this, okay, this here is the multiplicity. This is called the statistical multiplicity of the particular state within quotes. We are considering the overall state of the ensemble. Okay, we are considering the overall state of the ensemble, and that state is characterized by these ni's. Okay, so if you define n1, n2, n3, so on. So Ritvik, did you not understand something, or do you have a question?
No, sir, it was by accident.
Okay. Yeah. So this statistical multiplicity, what we counted here is in how many different ways can we realize this particular combination of n1, n2, n3, so on. And what second law of thermodynamics says is that, or at least what Boltzmann discovered, was that it is the Kb ln of this, let's call it m. We called it multiplicity, so let's call it m. The Kb ln m of this multiplicity is the entropy of this system, entropy of this ensemble. Okay, that was Boltzmann's definition of entropy of this ensemble. Now, what he said was, let us now maximize this entropy. Okay, so let us maximize m. Right? Because that is what thermal equilibrium is. When you take the system and get it into thermal equilibrium, because the process of reaching thermal equilibrium is very often an irreversible process, in the sense that I just described to you earlier, that the two systems initially may be of different temperatures, but once they reach thermal equilibrium, you don't see this reverse process happening spontaneously. You have to do a lot of work to separate the temperatures of these two again. So according to the second law of thermodynamics, in the language of this statistical multiplicity and this definition of entropy, a state of thermal equilibrium is one where the statistical multiplicity, or thereby the entropy, will be the maximum. So he set about maximizing this quantity m. But you can't just maximize. I mean, well, I can choose very, very, very large n's maybe, and n1s and n2s and n3s, and I'll keep going. No, you have constraints. the total energy of the system has to be constrained to E, and the total number of the systems in the ensemble has to be constrained to capital N. So the problem is to maximize a particular function with of these N1s while keeping the total number of systems constant and the total energy of the systems constant. Okay, and usually this is done when you have a function that you want to optimize along with constraints. We use the method called Lagrange multipliers, where we take the function that we want to maximize. So in this case, we want to maximize m, but since entropy is defined as the logarithm of m, we will actually maximize ln of m, which is equivalent to maximizing m. Okay, so consider the function. Sorry, there is some, yeah. So consider a function L, which is given by ln of m, and we want to maximize this subject to two constraints. So we say this is alpha times n minus summation over I ni, and remember that this term is identically 0 because that's a constraint, plus beta times E minus summation over I ei ni. All we have done is the statement that we are maximizing ln of m and the statement that we are maximizing L is identical because these two are anyway identically 0. We did not really add anything. We just wrote it in symbolic form using two factors alpha and beta, and the factors are multiplied by zeros because of the constraint. Then we want to now maximize this. But before we do that, we write this as ln n factorial by n1 factorial, n2 factorial, so on, plus alpha n minus summation over I ni plus beta E minus summation I ei times ni. Okay. Now, another advantage of writing it as the logarithm is we have something called the Stirling approximation, which you will use a lot in statistical physics later, but it's even for non-physics majors, this is an important approximation to learn. So ln of n factorial, limit n going to infinity. Okay, let us actually write some other letter here for any little n. Okay, n going to infinity can be written as n ln n minus n. Okay, in other words, ln n factorial is approximately, if you ignore for very large n, you can even ignore this and write this as n ln n. Therefore, n factorial grows as n power n. It is a super exponential function. It doesn't grow exponentially, it grows much faster than exponential. That's good to keep in mind. And so this approximation is called the Stirling approximation. So let us now use that to simplify that first term. Now the assumption is that n goes to infinity. So we write ln of n factorial minus ln of n1 factorial, or summation over I ln of ni factorial. This is what the first term is, subject to plus alpha n minus summation over I ni plus beta E minus summation I ei ni. Okay, we still haven't used any approximation, and this is the cost function L, or the optimization function L. Now we use the Stirling's approximation on each of these terms. So in addition to thinking that capital N is very large, we are also assuming these ni's are also very large. Okay, both ni's, and thereby capital N, they are all large numbers. Now if you use that, you get n ln minus n minus capital N minus summation over I ni ln ni, I'll write it in square brackets, minus summation over I ni, okay, plus alpha n minus summation over I ni plus beta summation over I e minus I ni ei. All right, now we maximize. This is L. If you maximize L, that is, you want this to be 0. Mathematically, that's the only way we know to compute a maximum. Take the derivative with whatever variable you are trying to maximize this with and make it 0. Okay. If we want to maximize M, yeah, but it's subject to the constraints, right? We may not be able to have the constraints satisfied by such a naive choice of n1 equal to n2 equal to so on up to equal to 1. That is the whole point. Do you get that, Anjane? That the constraint may work for capital N itself, but it should also work for capital E. That is the whole point.
Sir, but in that case, E will be E1 plus E2 plus E3. So what is problem in that? I mean, I don't see a clear problem in that.
No, in the sense you want the system to have a particular E, and each of these states may or may not have may or may not have energies which add up to capital E, meaning capital E is something that you are specifying. Okay. If you specify capital E in your choice of the numbers, the capital E will only be E1 plus E2 plus E3 so on. What I'm saying is I'm
Yes.
specifying capital E and I want to choose NIs accordingly. Because that is how most thermodynamic systems are, that you have certain internal energy and you are trying to understand what the various distributions are of the microscopic constituents. That is the exercise, that the underlying motivation.
Sir, I was thinking like if say if we assume that the total E capital E is 1 joule, so E1 can be 0.1 and E2 can be 0.2, and they can be further smaller values so that the total sum is 1. So that can be achieved. That is not impossible, right?
EIs are fixed, yes. So yes, EIs are fixed because EIs correspond to the states A1, A2, etc., etc. E1 is the energy of A1, E2 is the energy of A2, and so on. So the energies EIs are fixed. And the system, I'm telling you that the system can only exist in these states, A1, A2, so on, and so forth. So these EIs are fixed and the total energy is fixed. And you are trying to choose Ni such that two constraints are satisfied. Summation over Ni's is N and summation over NiEi is E. And when you have such a constraint, you can't make such trivial
Okay, sir. Okay.
are working with finite temperatures and
Excuse me, sir.
Excuse me,
Not
sir.
audible.
For some reason I got muted. I just got muted. So take this expression, write down delta L by delta Ni equal to 0 and verify that this is what you get. Minus ln Ni minus alpha minus beta Ei equal to 0. Okay. And if you just write down this carefully, you get e to the power of minus alpha times e to the power of minus beta Ei, where beta is some constant, which was actually one of our Lagrange multipliers. Okay, there were two Lagrange multipliers. Whenever, if you have two constraints, you will have two Lagrange multipliers in the problem. And beta was one of the Lagrange multipliers that was a cofactor of this energy term. Okay, so what Boltzmann discovered was that this Ni, and if you see Ni by N, is the probability that this, that the system is in state AI. Okay. So the probability that the system or the ensemble, the probability that you will find the systems in the ensemble in a state AI was found, according to Boltzmann's derivation, to be e to the power of minus, to be proportional to e to the power of minus beta Ei. Now this derivation is a direct consequence of the second law of thermodynamics, and therefore this Gibbs principle, the Gibbs-Boltzmann principle, or the Gibbs-Boltzmann distribution, is a direct consequence of the second law of thermodynamics. Okay, but there is also something very special. This probability that the system is in a state AI, and I did not really say anything about the state AI other than that the state AI has an energy Ei. Right? This state AI can have various other parameters. It can have some angular momentum, it can have this and that. But the derivation that I just did, I put a constraint only on the total energy of the system, and thereby only the energy of the state Ei entered the calculation, and therefore the probability that the system is in the state AI is a function only of its energy and nothing else. Now this may seem rather uh, an underhanded sort of derivation where we put in a constraint on the energy, and therefore the probability that this ensemble has systems when the state AI came out to be only a function of the energy of the state AI, which is Ei. But it is not really that unrealistic, meaning it is not some special case. Most statistical systems or most complex systems for which we need to apply statistics are such that energy is pretty much the only conserved variable. Okay, for you all know that there are these various principles of conservation of linear momentum, angular momentum, and energy, right? So a dynamical system or a mechanical system like a two body oscillator or a two body gravitational attraction or a many body gravitational attraction, these are complex systems. As the number of bodies increases from 2 to say the Avogadro's number, this becomes a very complex system, and you cannot really study the system dynamically. The three body problem itself is not solvable. So forget about the n body problem. Now, when n is Avogadro's number or several Avogadro's numbers, then it's virtually impossible to do a dynamical closed form or even a numerical simulation of this solution of this problem. and we have to take recourse to statistics. And what this Gibbs principle tells you is, or the underlying assumption is, that for most of these very complex systems, the only variable that is truly conserved is the energy. Okay, and that is
Sir, you are muted.
hello, can you hear me? Hello.
Yes, sir, we can hear
Yes,
you.
sir, you are audible.
Yeah, I think there is some internet issue because of which let's see, stop presenting, start presenting. All right, so what I was saying, hello, can you see my screen?
No, sir.
Yeah, this is stupid, I don't know what is happening. Until the other day it was okay, but suddenly there was some, since last class I've been having issues. Okay, I think I'll have to log out of this other device and then come back again. Yeah, let us. Can you hear me now?
Yeah, I think, yeah, I can hear you.
Okay. Can everybody hear me? Hello.
Yes, sir, you are audible.
Okay, thanks. Yeah, and you can see my screen, right?
Yes, sir.
Yeah. So what we saw here was that the probability that the system is in a state AI is essentially proportional to is a function only of its energy, EI. Okay, and no other factor. And of course, this beta is just the temperature. Now, let us look at this was sort of an abstract analysis where we did not say what AI is and what EI is, but we can do something more concrete. Let us now consider an ideal gas. Okay, let's consider an ideal gas with n molecules. Okay. Now, for simplicity, let's also consider a monatomic ideal gas. And we said that since these particles are moving about according to Newton's laws, each particle, to specify the state of the system, we need to specify the coordinate of the particle as well as its velocity. And since the particle has a mass m, we can also specify the coordinate and its momentum pi. Okay, so a complete specification of the coordinates and momenta of all particles specifies the system. Specifies the system, state of the system. Therefore, state of the system will be specified by the following numbers: x1, x2, so on up to x capital 3n. Now these x1, x2, x3 could be the xyz of particle 1. x4, x5, x6 can be the xyz of particle 2, and so on, because we have 3 dimensions. And then we have p1, p2, so on up to p3n. Okay, so if you take n particles moving about in a certain region of in a volume, there are essentially 6n initial conditions, 6n initial conditions that need to be specified to solve the full dynamics of the system. Okay, now I don't know why my screen share is not updating. This is ridiculous. I mean, I get so. Start broadcast. All right. Yeah. So we need to specify 6n initial conditions. Therefore, this dynamics we can think of a gas with n molecules as evolving in a 6n dimensional space. Okay, 3 dimensions is the physical space in which each gas molecule is moving. But if you look at the dynamical space of all n molecules, at every point you need to specify 6n values so that you can evolve the system, that is, solve the differential equation and go to the next point. So this 6n dimensional space is called the phase space of the system. Phase space of the system.
Sir.
Okay. Yeah.
Excuse me, sir. So why only these 6n conditions are sufficient to specify the state of the system? Like
Yeah,
what about the
because
acceleration particle?
you don't need the acceleration, right? Because Newton's laws solve for the acceleration once you know the forces. Newton's laws say that m times d square r by dt squared is the F net, the net force acting on that object. right? So if you now consider such a Newton's law equation for each particle in this box, to solve this equation, you need to specify r at any time t naught, and r dot at any time t naught. If you have these two pieces of information, assuming we know the forces, you can solve this equation exactly.
So yeah, exactly this. So we need to know the force, right? We need to know the force acting on a molecule because
Yes,
otherwise we cannot solve for
yes,
the equation of Newton.
exactly, exactly.
So won't we also need to specify the forces? How are we
No,
going to?
the forces are anyway part of the physical description of the system, but that is not a, the dynamics of the system is defined by the forces. I agree. But once you know the forces, you still want to know how these positions and velocities are evolving with time, right? Meaning, if I hit a particle at a given point of time at a given location on the billiards board, how will this move about? Billiards table, how will this ball move across the table? It'll go inertially to a certain point where it hits a wall, then gets specularly reflected there, then goes a certain distance again uniformly, etc., etc., etc. This entire trajectory can be worked out if I specify the initial location of the ball, and I also have to specify the force that I'm applying on it, and the region, the spatial region in which the ball is moving, that is like the volume of this.
So I cannot
How
hear
this
you.
particle. Oh man, this audio is giving a lot of problem today. Can you hear me?
Yes, and now it is. Now you're audible, but in between it was like you were not audible.
Okay, okay. I think there is some net issue. I have to figure this out. The last two, and the institute's internet is also rather finicky. So yeah, in any case, what I'm saying is forces are part of the definition of the problem. Without knowing the forces, you can't write Newton's laws. And once you know the forces, you write down the Newton's laws and you have to solve for the trajectory of this particle. And by trajectory, we mean what is the position at every instant of time and what is the velocity or momentum at every instant of time. This information, this trajectory is in the position and momentum space. So the trajectory of the overall system with all n particles is in a space of 6n dimensions. And this space is called the phase space. Is that clear?
Sir, but now you said that we need to know the force acting on each molecule, right? That is given in the
Yes.
problem. So
Yes.
wouldn't we be getting a sort of 9n space because we have
Fine.
this force
No, but the
F1?
forces are not changing, right? The forces are constant, or meaning you know the forces. If two particles come together, exactly what force acts is something that you think of it like a simulation. Okay, think of it like a simulation. The force is like a function that you call whenever two particles come within a certain distance. You call this particular function. The function is defined by you, and the inputs of that function are the spatial locations of the particles and the velocities of the particles, always, because all these forces depend on the locations of the particles. If they are central forces, okay, just hold on, I keep
Okay,
getting,
okay, sir.
yeah. Hello. Yeah. So this system moves in a 6n dimensional space. In this sense, the forces have to be defined. Otherwise, you cannot do anything with Newton's laws. Okay.
So, and the forces need to be time independent also, right?
Sure. Sure. Even if they are time dependent, you should know how they are time dependent beforehand. You
Oh,
can
okay.
you can solve Newton's laws even if the forces are time dependent, but you should know
But the
how they are
expression
time
should be
dependent.
known.
Yes. Yes. So that is the whole, you know, those are the inputs that go into Newton's laws. Forces are the inputs that go into, if you think of Newton's laws as a black box, the inputs are the forces and the initial conditions. The forces set the dynamics and the initial conditions evolve. And we are
Yes,
interested.
sir, now I get.
Yeah. So this evolution of the initial conditions from the initial point to the final point happens in a 6n dimensional space, and that is called the phase space of the system. And the energy, okay, of a particular state. Now the state AI, that I defined in abstraction earlier is essentially a set of coordinates in the 6n dimensional space, x1, x2. Let's say it's the xn, 3n, and then p1i, so on up to p3ni. This defines these 6n values define the state AI. Okay, and there is an energy E I, which is then a function of these x1i, x2i, so on to x3ni, p1i, p2i, so on up to p3ni. For example, for an ideal gas, EI will be equal to half m I x I dot squared summation, which is pi squared by 2mi, right? Where I goes from 1 to 3n. So all we know about the energy of the ideal gas is that there is no potential, so there is no term in the energy which depends on the coordinate. Now let us say we take n oscillators in 3 dimensions. Okay, we have n oscillators which oscillate in 3 dimensions. For n 3-dimensional oscillators, this energy function EI will not only be pi squared by 2m, this will be the kinetic energy plus half ki xi squared, where ki is the spring constant of that oscillator and xi is the extension of that whatever spring is holding those two particles. Okay, so the energy of a collection of n oscillators, each oscillating in 3 dimensions, would be something like this, where I goes from 1 to capital 3n. So in general, for any system, the energy of a state AI is a function of its coordinates and momenta. Now go on. Question?
Sir, why are you assuming that these are simple harmonic oscillations?
Well, I'm not assuming anything. I'm considering such a system. For other complicated systems, you have to write the energy function accordingly. For an ideal gas, this would be the energy. For a collection of capital N oscillators, this would be the energy. If you want a collection of magnets in a magnetic field, you would have something like summation over I, n magnets, let us say, minus mu I dot B. Why not? Right? For n magnets.
Oh, okay, sir. I realized.
Okay. Now,
Sir,
even these magnetic moments that I wrote here of each of these magnets, they can be modeled in terms of some underlying dynamics. Classically, any system property is a function. I'm not saying things like temperature, or even temperature is a function of the internal energy, and the internal energy is a function of the momenta and the coordinates. Okay, so for any classical system, EI is usually a function of xi's and pi's, all the xi's and pi's. So it's x1, x2, so on up to x3 and I, and then p1 up to p3 and I. Yeah, Anjane, you had a question?
Sir, in the expression for energy, you have written that summation pi upon 2mi. So there will be only n particles. So we are summing from I to 3, and how is
Yeah,
that
because there is.
reasonable?
Yeah, so what I mean is I'm actually summing from x, y, z of. So the x, y, and z for a particular particle will have the same denominator. That's what I mean.
Okay, sir.
Different mi's can be the same, right? I mean, in 3 directions, you will have the same mi that enters the px squared by 2mi plus py squared by 2mi plus pz squared by 2mi. Px, py, pz can be different. That is what I'm summing over.
Okay, sir. And sir, if we consider the rotational energy in this, then the moment of
Yes.
inertia will be
Now,
different in different directions.
exactly. Classically, rotation energy will depend on the angular velocity, which will then you have to define it in terms of the angular momentum. All those things. This is only for translation. There will be other degrees of freedom, but they will all, in principle, the only ingredients that go into even defining the angular momenta are the momenta and the coordinates of the particle, right? It's r cross p for every particle.
Yes, sir.
And that's the only angular momentum that you can define for a classical particle. For an extended object, you take the summation of all sigma of r cross p for each particle with respect to some axis or a point, and then you can write it in terms of a moment of inertia matrix and all that. All those are details, but if you take a system to be a collection of particles, an Avogadro number of particles, let us say a 1 mole of iron bar magnet, that has an Avogadro's number of particles inside, and those Avogadro's number of particles are, you can define their positions and velocities and various things, and they are like, of course, the problem of ferromagnetism is actually not, you can't really explain it classically, but really explain it classically. But I'm just giving you an example that even extended systems, you can define the coordinates and momenta of the underlying particles, and classical mechanically, in classical physics, those are the only informations that you need to know to work out the dynamics. So the phase space is usually 6n dimensions when you have n particles in 3 dimensions. Any question?
Okay, sir.
Sir,
All right. Yeah.
sir,
So
you have written that the energy of the ith state is a sum from I is equal to 1 to 3n. So should the subscripts be different?
no. Yeah. It's I don't. Yeah. That's I am indexing, let's say J. This is a different subscript. In general, for systems like this, the energy is, there is an infinite range of energies possible for the system, because xi's and pi's can actually be very, very large. So in principle, any energy is possible. There are only special kinds of systems where the energy is bounded, and surprise, it is those systems which have bounded energies which exhibit negative temperatures, like the ones I talked about earlier. So For all practical purposes, 99% of the time we will, unless otherwise specified, we are considering a system where this energy is an unbounded quantity from above. There is no bound from above, but there is usually a bound from below.
Yes, sir.
Okay, so it is a semi-infinite sequence bounded below. All right, so all I wanted to say, I will conclude with this point, that the energy of a state Aj, which is Ej, is usually a function of 6n variables. Therefore, if you now want to compute, so x and p are continuous variables, that is the coordinate of a particle inside a volume is a continuous variable that goes from, let us say if it's a cubic volume and the side of the cube is say from 0 to L in all directions, then the coordinates will continuously vary from 0 to L along x, y and z. And the momenta can actually take very large values, and thereby the energy can keep growing indefinitely even for a finite volume gas like this. Okay, now the probability density you can define, we defined a probability earlier. So if you define a probability density, okay, that the particle or that the system, that the collection of n gas molecules is around this particular point in phase space, okay, you have all studied probability, so this is the probability density, that it is the probability. So what I have written here is the volume element of phase space. This is dx1, dx2, so on up to dx3n times dp1, dp2, so on up to dp3n. I'm assuming simple Cartesian sort of 6n dimensional space, and this is the probability density of finding the particle at a particular, or finding the system, all n particles at these coordinates and momenta. Now the probability of finding the system in a tiny volume dx1, dx2, so on up to dx3n times dp1, dp2, so on up to dp3n is the product of this density times the volume element. That will be equal to e to the power of minus beta e, which is a function of x1, x3n, p1 to p3n, okay, times dx1, dx2, so on up to dx3n, dp1, so on up to dp3n, divided by the normalization constant will obviously be a multiple integral over all x1 to x3n, dp1 to dp3n times the same probability. So this is the way in which you actually, this is the expression which you use to compute the probabilities in reality. Okay, given a system of ideal gases, given a system of molecules in which form an ideal gas, if you want to compute the probability density or a probability in a finite volume, this is how you do this. Now we will stop here. In the next class, what we will do is we'll start from this point and apply this to a system of molecules comprising an ideal gas and see how to work with this sort of a formalism and derive the equipartition of energy. Okay, we will derive the equipartition theorem of energy using this fundamental principle, and then we will proceed to black body radiation. I want to hold, instead of office hours this Friday, I want to actually hold a class because 2 weeks down the line, there is going to be a break. And I want to kind of compensate in advance for that. Is it okay with everyone if I hold a class on Friday morning at 9:30?
Yes, sir.
Yeah. And later on, we will have a break on a Monday or a Wednesday, so it will compensate for that. Yeah. Okay
Sir,
then. Yeah,
Uh,
questions?
Sir, why will
sir,
be
how
having
does
the break?
Sorry?
Why will be having the break?
Oh, because I have some travel coming up.
Oh, sorry, sir.
Yeah. I'm not saying there is a scheduled break or due to some holiday or something, but I have some travel coming up. So it's very likely that I'll have a break.
sir?
Yeah.
Hello. So, how is the probability density equal to e raised to minus be? It should be the probability, right?
No, though. So in the case that I defined simply in the beginning, I actually considered these energy values to be a discrete spectrum, meaning the energy values are only some discrete states A1, A2, A3, so on are possible. But the way I have formulated this ideal gas problem, the molecules are moving continuously, so the energy can also have a continuous set of values. And whenever you have such a continuous variable, you have to specify it correctly in terms of a density, probability density. And this is the way to define that probability density. The probability density of finding the system of gas molecules with coordinates x1, x2, so on up to x3n and momenta p1, p2 up to p3n times the tiny volume element dx1, dx2 up to dp3n in phase space. This volume element is taken in phase space times the density of the phase space point, the probability density at that phase space point. That will be equal to e to the power of minus beta e, where e is calculated at that point because the energy is a function of the 6n dimensional phase space coordinates and momenta. So the energy is a function and you evaluate that function at that point times the volume element divided by the normalization factor. That is the probability. That's the correct way to define it for a continuous energy spectrum.
Okay, sir.
Yeah. So this these sort of you are all familiar with probability densities, right? I mean, you must have encountered probability densities in some course
Yes, sir. This course, like this semester itself.
this semester itself. Yeah. So this is the correct way to handle probability densities. For simplicity, we work with probabilities, but they are only defined for discrete events.
Yes, I got it, sir.
Yeah. All right. So we'll meet on Friday morning and we'll continue on this and we'll try to look at black body radiation and then go into
Thank
Planck hypothesis and from then on we'll move into quantum mechanics. So this part of thermal physics is actually very foundational. Even those who don't take up physics. For example, in my undergrad, I worked in a project on DNA sequencing analysis and which had nothing to do with physics per se, but the probabilities of various transcription sites and other things are very often calculated using such a Gibbs distribution. So there is some sort of an energy function and this Gibbs formula keeps appearing in various contexts. So it's good to understand how this comes about. Okay. Even for those of you who don't end up doing physics, of course, chemistry, all of chemistry, uses these aspects of statistical physics, but also many biological systems. Okay, then. So let us pause here and we'll continue on Friday.
you, sir.
Yeah.